Imagine taking the air you are breathing right now and turning it into a substance that can freeze ice cream in 3 seconds and make a banana tough enough to hammer nails. This is not magic. It is liquid nitrogen. Every second, it is used in medicine, science, the food industry, and in some top-secret experiments. Temperature, -321 degrees Fahrenheit. 1 sip and you lose part of your stomach. 1 breath and you unlock tomorrow's technology. How does the coldest substance on Earth get made from regular air? How is it transported, stored, and used? And why can it save or destroy? Watch closely and prepare to be amazed. It all begins with air. Yes, the very same atmospheric air that surrounds us. This happens inside industrial air separation units. These systems come in all sizes, from massive factory installations to mobile units for medical use. Air is sucked in using compressors. Then it passes through filters. First, coarse filters that remove dust, insects, and pollen. Next, fine filters get rid of moisture, carbon dioxide, and other impurities. Once cleaned, the air is compressed using powerful machines, increasing both pressure and temperature. Then, it is gradually cooled in heat exchangers. When the high-pressure cooled air moves through a narrow nozzle into a low-pressure chamber, it expands rapidly. That sudden expansion causes a major drop in temperature. This is the key moment. The gas becomes cold enough to start condensing into a liquid. This process repeats several times. Each cycle drops the temperature further. Eventually, nitrogen reaches its liquefaction point. This technique does not work with every gas, but it is perfect for nitrogen. Thanks to this, we can create liquid nitrogen from ordinary air. Once the air is chilled and liquefied, it goes through fractional distillation. This process separates the liquid mixture into components based on their boiling points. Inside a special distillation column, the liquid air is gently reheated. Nitrogen has the lowest boiling point, around -320 degrees, so it evaporates first and rises to the top. Oxygen boils at -297 degrees, so it evaporates later and does not climb as high. Argon, with a boiling point around -302, settles somewhere in between. The column forms a thermal gradient, colder at the top, warmer at the bottom. The gases evaporate and condense over and over, becoming purer with each cycle. It all works without additives, automatically, and with minimal losses, thanks to precisely managed pressure and temperature. Since nitrogen makes up roughly 78% of air, extracting it takes powerful equipment, a complex network of pipelines, and exact temperature control. Once separated, liquid nitrogen is stored in special vessels, cryostats, or Dewar flasks, which look like futuristic thermoses. These vessels keep temperatures low and prevent evaporation. They are not just metal barrels. They have double walls with a vacuum in between to block heat. Some also include reflective coatings to minimize radiant heat loss. These containers can preserve liquid nitrogen for several days to several weeks, depending on volume, insulation, and how often they are opened. Often, nitrogen is used right on site. For example, medical facilities use liquid nitrogen for cryopreservation of cells, embryos, vaccines, and tissues. In the food industry, it is used for flash freezing. Contact with liquid nitrogen instantly freezes food, locking in texture, taste, and shape. But when it needs to be transported, preventing evaporation is critical. That is because nitrogen quickly turns back into a gas. Portable dewars, cryotanks, and cryotank trucks are used. Small dewars are handy for labs and clinics. Cryotanks are massive, like giant gas tankers, and are hauled by trucks with special mountings and ventilation. Cryotank trucks are purpose-built vehicles with insulation and pressure regulation to avoid explosions from expanding gas. Sometimes, liquid nitrogen is produced directly on site, at large research centers or hospitals, to avoid reliance on deliveries. How did humanity tame one of the coldest, most inert substances on Earth? It all began with nitrogen. Discovered in the year 1772 by Scottish chemist Daniel Rutherford, who was studying air and found a gas that could not sustain fire or life. That was nitrogen, colorless, odorless, inert. But liquefying it required cold and pressure, and humanity needed more than 100 years to figure that out. The first liquid nitrogen was produced in 1883 by Polish scientists Zygmunt Wroblewski and Karol Olszewski. They built a system that cooled air so much that nitrogen, its main component, turned into a liquid. That was a breakthrough. In the 20th century, cooling tech advanced fast. Scientists improved gas liquefaction methods and eventually developed the Joule-Thomson cycle, which relies on pressure drops to efficiently liquefy gases. In the 1930s and 50s, liquid nitrogen made its way into industry and medicine, starting in labs, then into surgeries, biobanking, and physics experiments needing ultra-low temperatures. Today, liquid nitrogen production is a global-scale operation. It is made in massive air separation plants around the world. What was once just background gas, making up almost 80% of air, has become a superstar of industrial science. Some chefs even make ice cream live, pouring cream into a bowl, adding liquid nitrogen, mixing, and voila, instant dessert. The cold is so intense, it freezes the treat in seconds. Dip a banana in liquid nitrogen for a few seconds, and you can hammer nails with it. Seriously. Want to try? Inhaling cold nitrogen vapor can temporarily change your voice, like helium, but deeper. But do not try this. It is dangerous without protection and special equipment. Some people have dipped old socks into dewars of liquid nitrogen. Result? The fabric becomes brittle like glass and crumbles in your hands. A perfect way to destroy evidence. If you are a sock. Pour liquid nitrogen on a warm floor, and it turns into a dramatic cloud. It vaporizes instantly, making you feel like you are stepping through a Hollywood portal. What should you never do with liquid nitrogen? Even if it looks cool, never stick your hand into it. Online videos show people dipping fingers and pulling them out unharmed. That is the Leidenfrost effect. A brief protective vapor layer forms around the skin, but if you hesitate for a second too long, hello frostbite, do not try it. Seriously. Never drink it. Yes, that happened too. In several restaurants, smoky desserts were served with a drop of liquid nitrogen. One careless guest sipped before it had fully evaporated and lost part of their stomach, literally. Afterward, several countries banned such stunts. Do not pour it on your bathroom floor. The vapor looks cool, sure, but tiles can crack from thermal shock. Plus, the risk of suffocation in a small space is real. Nitrogen displaces oxygen. Do not pour it in the toilet. Not because it will definitely break, but it might. And because pipes can burst. Some TikTokers have proudly frozen their plumbing. Utility crews must love them. If you are not an engineer or a molecular gastronomy chef, do not try freezing food or fruit from the inside. Liquid nitrogen can rupture the skin and explode in your hands, especially with high moisture items. So yes, liquid nitrogen is amazing, but it is also incredibly dangerous. Respect the frost. Imagine a company at the center of a major scandal, but instead of fading away, it turns the challenge into an opportunity. Fairlife went from facing accusations of animal cruelty to becoming a leader in the dairy industry by implementing new ethical standards and winning back consumer trust. This is a story about how a crisis can become the starting point for positive change. Ready to learn how they managed to change the game and set new industry standards? Let's dive into this fascinating journey of transformation. Like any production process, Fairlife's manufacturing begins with collecting the main ingredient, milk. Fresh milk is sourced from farmers who adhere to high standards of animal welfare and product quality. Once the raw milk arrives at the plant, it undergoes the critical process of ultrafiltration. Ultrafiltration is a key stage in Fairlife's milk production that allows the separation of proteins, calcium, lactose, and other components. This process serves multiple purposes, removing some of the water from the milk, which makes the product more concentrated, significantly reducing the lactose content, making the milk suitable for people with lactose intolerance, and increasing the protein content by about 50% compared to regular milk. The ultrafiltration process is carried out using special membrane filters. These filtration systems utilize ultra-thin membranes through which the milk is passed under pressure, removing excess water and concentrating essential nutrients. After this, the milk moves into separators that help further divide the milk's components into different fractions, ensuring the right concentrations of protein, calcium, and fats are achieved. The next stage in Fairlife's production is fortification. This is the process of adding extra nutrients, such as vitamins and minerals, to the milk to boost its nutritional value. Common additives include vitamins D and A, calcium, and other beneficial components. These nutrients are introduced in either liquid or powdered form using special mixers. Before being added, the supplements are dissolved to ensure even distribution throughout the milk. Here's how the process works. Dosing devices calculate the required amount of additives based on the volume of milk being processed, which varies depending on the plant's capacity. The machine then measures the correct amounts of vitamins and minerals and introduces them into the ultra-filtered milk. Afterward, a giant mixer, known as a homogenizer, blends the liquid thoroughly to ensure even distribution of the additives, preventing clumping or uneven concentrations. Once mixing is complete, samples are taken for quality testing. This timely quality control step ensures that the nutrients are evenly distributed and meet established standards. The next stage is pasteurization. This is an automated process in which milk is treated at high temperatures to eliminate harmful bacteria while maintaining its freshness and nutritional value. Honestly, I was amazed at how much happens at the plant. You might think it's as simple as getting the milk from the farmer, bottling it, and that's it, right? But meanwhile, the ultra-filtered and fortified milk flows through pipes into the pasteurization block, where it pours into prepared containers. In the pipes, the milk passes through heat exchangers, where it's quickly heated by hot water or steam to 170 degrees Fahrenheit for 15 to 20 seconds. This quick heating process kills most pathogenic organisms. As for the remaining few, well, nothing is ever 100% sterile, just something to live with. After heating, the milk is rapidly cooled to about 40 to 42 degrees Fahrenheit, which helps preserve its freshness and prevents bacterial growth. The cooling happens in the same exchanger, but this time using cold water that circulates around the pipes. The pasteurized milk is then transferred into sterile storage tanks, where it waits until it's ready to be packaged. The finished milk is packaged into special airtight containers that ensure freshness and long-term storage. By the way, here's a personal tip. Always check the seal of the packaging before you buy it. Once, I failed to do this while visiting my parents for a family dinner, and let's just say the upstairs bathroom got a lot of use. But that's another story. After pasteurization, the milk is transferred from storage tanks to the conveyor belt through pipelines. There, it enters an automated packaging system that controls the entire process. On the packaging line, machines automatically supply and form either cardboard or plastic containers. The packaging is sterilized with ultraviolet light or steam to kill any potential microorganisms. Fairlife milk is dispensed into the prepared containers by high-precision dosing machines, ensuring that each container receives the exact same volume. Once filled, each container is hermetically sealed to prevent air from entering and to maintain the milk's freshness. Depending on the type of packaging, sealing is done using either adhesive or heat. After the containers are securely sealed, important information like the production date, batch number, and expiration date is printed. This labeling is done directly on the packaging line using either a laser or inkjet printer. The packaged containers go through automated sensors and cameras, which check for defects, proper sealing, and compliance with standards. Once inspected, individual containers are grouped into larger bundles or boxes for easier transportation. Robotic systems swiftly and accurately assemble these group packages. The finished bundles are then automatically stacked onto pallets, ready to be stored in the warehouse or sent directly to retail locations. I swear, friends, I've never seen packaging quite like Fairlife's anywhere else. It's so futuristic. It stands out from regular milk cartons as if it was dropped straight from a spaceship onto your table. Fairlife processes millions of gallons of milk each year to meet the demand for its products in the United States and other countries. Thanks to ultrafiltration, Fairlife milk contains 50% more protein and 30% more calcium compared to regular milk. Each serving of Fairlife provides approximately 13 grams of protein per glass, making it popular among people who follow a healthy lifestyle. Fairlife is actively promoted as a healthier alternative to regular milk due to its high protein content and reduced sugar levels. The company works with small family farms, ensuring high-quality milk and supporting the well-being of farming families. Thanks to its specialized processing, Fairlife milk has a longer shelf life, up to 90 days, compared to regular milk. The company emphasizes environmental responsibility by using technologies that reduce water and energy consumption during production. Fairlife quickly became one of the leaders in the ultra-filtered milk market thanks to its innovative approach. However, the company found itself in the spotlight after allegations of animal cruelty at its supplier farms surfaced. In response, Fairlife took action to improve animal welfare and implemented new standards for monitoring its farming partners. The company is actively working to regain consumer trust by introducing initiatives aimed at enhancing animal well-being. Fairlife continues to expand its product line, adding flavored milk options, yogurts, protein drinks, and other dairy products. Did you know that over 10 million cakes are produced worldwide every day, with ingredients traveling from every corner of the globe? In this video, we'll dive into the fascinating world of massive conveyor belts and fully automated production lines, where simple ingredients are transformed into sweet masterpieces in just minutes. Get ready to uncover the industry secrets you never knew existed. Cake factories in the United States and worldwide purchase ingredients in volumes that match the scale of their production. They typically sign contracts with large ingredient suppliers, such as producers of flour, sugar, butter, eggs, dairy products, and flavorings. These suppliers can deliver consistent, large-scale shipments and often adhere to strict quality standards, which is crucial for maintaining the taste and quality of the final product. Core ingredients like wheat flour are usually bought from large manufacturers or cooperatives, while specialized ingredients, like flavorings or colorings, may be sourced from specialty companies. Logistics companies deliver these products directly to factories, often in refrigerated or sealed containers to keep everything fresh. Some ingredients like chocolate or exotic fruits are imported from producing countries, chocolate from Latin America for instance, since this can offer better quality or pricing compared to local sources. Imagine that the ingredients in your dessert might have traveled from nearly every part of the world. Modern cake production is fully automated, with ingredients added to the mixer via conveyor systems and dispensers, requiring no human intervention. For instance, dry and liquid ingredients are added using dosing and weighing systems. Each ingredient comes from its own container, fed through automated pipes or funnels that accurately measure and deliver the required amount into a large industrial mixer. Flour, salt, and sugar are dispensed from bins or containers through piping systems. They pass through dispensers that precisely control weight and quantity before being moved on a conveyor to the mixer. Butter, milk, water, and eggs are fed through special pump systems that control liquid flow, connected to dispensers that automatically add the exact amount of liquid ingredients into the mixer. At large factories, eggs are often used in the form of pasteurized liquid egg mixtures, stored in refrigerated containers. When whole eggs are needed, they are automatically cracked by special machines, with the shells separated, leaving just the egg mass for mixing. All these ingredients are then combined in the large mixer for blending. After mixing, the batter is directed to specialized dosing and filling machines that precisely measure and dispense it into baking molds. The batter from the mixer travels through a conveyor or pumping system to the dosing station. A holding tank or container is used to store the batter temporarily for convenience until the next step. Pumping equipment regulates the batter flow to ensure smooth, continuous transfer. At this stage, the dispenser carefully measures the batter volume that will be distributed into the molds. Dosing mechanisms are set to provide each mold with the exact amount of batter, which is crucial for achieving consistent cake sizes. Some systems use volumetric dosing, which measures batter by volume, or weight-based dosing to ensure the precise weight of each product. An automatic filling head distributes the batter into pre-arranged molds on a conveyor. As the molds move under the dosing head, the filling mechanism releases the required amount of batter directly into each one. These molds may be round or rectangular, depending on the product type. To avoid overfilling or underfilling, dispensers are equipped with a feedback system that adjusts batter amounts based on weight or volume data. Some filling machines have sensors that monitor filling levels and automatically stop once the correct amount of batter is reached. After the batter is poured into molds, the conveyor moves them into specialized industrial ovens. In large-scale production, tunnel ovens are used, where the conveyor with molds passes continuously from one side to the other. The baking temperature and time are carefully calibrated for each type of batter. These ovens are preheated to specific temperatures, typically ranging from 302 to 356 degrees Fahrenheit for cakes. The ovens maintain a steady temperature and control humidity levels, with modern models equipped with automatic temperature control systems to ensure even baking. It's crucial to maintain consistent heat distribution and optimal moisture levels during baking. Industrial ovens are often equipped with steam injection or ventilation systems to manage humidity, helping to create the perfect crust and texture for the cakes. The conveyor moves at a speed that allows each product to bake for the optimal amount of time, typically 20 to 30 minutes. Tunnel ovens feature adjustable temperature zones, so the batter rises at the beginning of baking and achieves an even color and texture by the end. This automated process allows for the simultaneous baking of thousands of cakes. After baking, the conveyor moves the molds with freshly baked cakes onto a cooling line, where they rest to stabilize their temperature. This step is crucial to prevent deformation and ensure perfect texture. Cooling usually happens via fans that blow cool air over the cakes. As soon as the cakes exit the oven, the conveyor transfers them onto a designated cooling line. At this stage, the cakes are still very hot, so gradual cooling is essential to prevent cracking. On the cooling line, fans or air conditioning systems blow cool air evenly over the cakes. The fans operate at multiple levels to cool the cakes uniformly from all sides, avoiding sudden temperature changes. I have to say, after my air conditioner broke this summer, I could have really used a tour like this to escape those 2 weeks without cool air. Some factories use spiral coolers, which are conveyors coiled in a spiral, allowing cakes to move upward and cool gradually along the way. This design saves space and provides ample time for gradual cooling, perfect for high-volume production. To prevent excessive drying, the cooling areas maintain an optimal humidity level. Some cooling systems even allow humidity adjustment to prevent the cake surfaces from drying out and to keep them looking fresh and appealing. Once the cakes are cooled, they move along the line where they are prepared for filling. All the necessary ingredients for the cream, such as buttercream, ganache, or other types of fillings, are pre-prepared and stored in large barrels or tanks. Automatic pump systems allow the cream to be transported directly from the tanks to the application area. This shortens the processing time and reduces the risk of contamination. The pumps maintain the required pressure so that the cream flows smoothly to the filling machines. The cakes are then lifted onto a special conveyor with a mechanism that has small fingers to gently hold each cake in place. Automatic machines apply the cream on the top of each cake, typically using sprayers or nozzles that distribute the cream evenly over the surface. If the cake has multiple layers, the mechanism automatically separates the cake into layers, applying cream between each one. This process also happens via conveyors that move each layer to the cream applicator and then return it to its original position. Fascinating, isn't it? After filling, the cake proceeds to the assembly stage. Here, special systems pick up each layer one at a time and stack them in the correct order. The machines may use different mechanisms, such as tongs, suction devices, or other technologies, to assemble the cake precisely without damaging it. Now comes the most exciting part, decorating the finished cakes. This is the stage that almost makes my mouth water. as it's nearly impossible to stay calm watching such artistry in action. After assembly, the cakes move to the decorating line. All the necessary materials, such as creams, glazes, fruit fillings, and other decorations, are prepared in advance and stored under controlled conditions. The cakes travel on a conveyor to a machine that automatically applies the glaze. This can be done using sprayers or injectors that form an even layer of glaze over the cake's surface. Next, a decorative pattern may be applied to the cake. This is achieved with special sprayers that create intricate designs using cream or glaze. Stencils or specialized machines may also be used to create embossed patterns automatically. Various decorative elements can be added to the cakes, including berries, nuts, chocolate pieces, sugar flowers, and other embellishments. Automated systems or robotic arms can carefully place these decorations, ensuring they're evenly distributed for a visually pleasing effect. During this stage, final touches like sprinkles of chocolate shavings, powdered sugar, or other toppings can also be added. Once decoration is complete, the finished cakes are transferred to an automated packaging line. Here they may be packed into boxes, wrapped in protective film, or otherwise prepared for transport. Pepperoni, cheese, or veggie? What kind of pizza would you pick? While you're dropping your choices in the comments, I'm choosing to head over to a massive frozen pizza factory. Did you know that over 2 billion frozen pizzas are sold worldwide every year? The United States leads in consumption, with the average American eating around 50 pounds of pizza each year. The process starts with mixing the ingredients for the dough. Large industrial mixers are used, which automatically add the precise amounts of flour, water, yeast, salt, sugar, and vegetable oil. The flour is stored in huge silos or containers, from which it flows through special pipes into the mixers. A sensor system carefully measures the exact amount of flour needed for each batch of dough. Water, oil, and other liquid ingredients come through dedicated pipelines, and each mixer is equipped with dispensers that automatically add the required amounts of these liquids. For smaller dry ingredients like yeast, salt, and sugar, separate dispensing systems are used to accurately measure and add them to the mixer at just the right time. Operators simply monitor the machinery and ensure proper dosing, while the entire ingredient delivery process is fully automated. The dough is mixed until it reaches a smooth, uniform texture, a process that usually takes about 10 to 15 minutes. After mixing, the dough is left to rest for a few minutes, allowing the yeast to activate so it becomes soft and elastic. After mixing, the large mass of dough moves down the line, where special automatic tongs or portioning blades separate equal pieces from the main batch. The machine is calibrated to a specific weight, ensuring each dough piece is the same size for consistent pizza quality. Each piece is then sent to the shaping station, where it's laid out on a conveyor belt or platform. Next, a machine with presses or rollers carefully but evenly flattens each dough piece to the required thickness. Modern production lines use sensors to monitor the diameter and thickness of each pizza base. If a piece is not flattened uniformly, the press machine automatically corrects it or sends it back for another shaping cycle. To create a nice edge, machines gently lift the dough's edges using special mechanical attachments or air jets that lightly blow around the perimeter, kind of like the iconic dress scene with Marilyn Monroe. This technique helps form a border that keeps the toppings from spilling out during baking. The finished pizza bases go through a final check as they move along the conveyor belt. Sensors inspect the shape and evenness, and only then are the bases sent to a light pre-baking step to set their shape. Through this process, between 3,000 and 5,000 pizza bases are formed every hour. That means the factory can produce up to 120,000 bases in a single day. The prepared pizza bases move along the conveyor into an industrial oven. The oven temperature is preset, typically ranging between 662 and 752 degrees Fahrenheit. The conveyor moves at a steady pace, ensuring each base bakes evenly. This high temperature allows for quick baking, about 1 to 2 minutes, depending on the thickness and size of each base. These ovens usually feature multiple heating elements placed above and below the dough to ensure even heat distribution. This setup creates a crispy crust that remains soft on the inside. During baking, the oven slightly humidifies the base surface with specialized steam nozzles, which help the dough stay tender within. After baking, each base passes through a series of sensors that check its color, texture, and thickness. If a base is under or overbaked, it's automatically removed from the line. The hot bases come out of the oven and are immediately moved onto a cooling conveyor. This cooling step is essential to stop any further baking. Cooling is managed by special fans that quickly lower the base's temperature before the next stage. While the pizza base is baking, a separate line is preparing the sauce. Tomatoes, spices, salt, sugar, and sometimes oil or other ingredients like basil or garlic are mixed together. The sauce is cooked in large vats where it's continuously stirred to achieve a smooth, uniform consistency. After cooking, the sauce is cooled down so it doesn't interfere with the following stages when it will be spread onto the dough. The par-baked pizza base travels along the conveyor to a saucing machine. This machine spreads the sauce evenly across the surface of the dough. To avoid overloading, a small border is usually left sauce-free, creating a clean edge on the pizza. The machine precisely measures the amount of sauce for consistency, so each pizza turns out identical. Interestingly, the manufacturer recently began reducing the amount of preservatives used in their frozen pizzas. After the sauce, the base moves further along the line to the station where other toppings are added. This step can be fully automated, although in some factories, workers are involved in the process. Toppings like cheese, pepperoni, mushrooms, vegetables, and olives are dispensed onto the pizzas using automated dispensers or specialized containers. Cheese is usually added first and in the largest amount to create a stretchy layer when baked. To ensure even distribution, special sifters or mechanisms gently sprinkle the toppings over each pizza. Vegetables, meats, and other components are added in precise proportions, so each pizza has a consistent flavor and appearance. After the toppings are added, the pizza moves on to a crucial step, flash freezing. It goes into a tunnel freezer where the temperature is kept extremely low, reaching -86 degrees Fahrenheit or even lower, just so you know. At this temperature, the pizza freezes within minutes. Flash freezing is important because it preserves the dough's structure, the texture of the cheese, and other ingredients, which helps maintain the product's original flavor. After freezing, the pizza bases, or fully assembled pizzas, move down a conveyor belt to the packaging line. Machines automatically position them correctly to avoid any wrinkling or deformation. The pizzas are typically wrapped in clear plastic film to prevent moisture loss and preserve freshness. This film is applied automatically, and special thermal elements quickly seal it along the edges, creating an airtight package. For certain types of frozen pizzas, vacuum sealing or an inert gas environment, such as nitrogen, is used to keep the product fresh for longer. In these cases, a machine either removes the air from the packaging or adds gas to prevent bacterial growth and oxidation. Once wrapped in plastic, the pizzas are automatically transferred to a machine that places them in cardboard boxes. This cardboard is usually sturdy to protect the pizza from damage during transportation. The machine folds the boxes around the pizzas and securely seals them with adhesive tape or special clips. Next, each box is labeled with product information, such as the name, ingredients, expiration date, and cooking instructions. This stage is also fully automated. A machine scans barcodes and prints labels according to the type of pizza. After labeling, each box goes through a quality control system. Sensors and cameras check for intact packaging, clear labeling, and the absence of any defects. If a box doesn't meet standards, it's automatically removed from the line. Following quality control, the pizza boxes are grouped into cases or stacked onto pallets. Robotic arms can automatically stack the boxes to save space during transportation. Before shipping, the pizzas are temporarily stored in large freezer rooms, which maintain a stable temperature until they are loaded into refrigerated trucks for transport to stores. And here's where you'll see something unexpected. Did you know that railroad tracks can actually bend like noodles? Yet in an instant, they become tougher than rock. Every year, over 15 million tons of steel are used to build these tracks. But how do we transform raw iron ore into rails that can withstand the weight of thousands of tons? Stick around to discover how cutting-edge technology and precision engineering are revolutionizing infrastructure. The process of manufacturing railroad tracks is a fascinating blend of advanced technology and heavy machinery. But it all begins with iron ore. This ore is mined either in open pits or underground. Open pit mining is used when deposits are near the surface, employing massive excavators and drilling machines. For deeper ore deposits, underground mines are excavated. Once the ore is extracted, it is crushed and refined through several stages to separate the iron and remove impurities. The enrichment process involves crushing, grinding, and either magnetic or flotation separation, which produces a concentrate with a high iron content. To create a strong and flexible alloy, carbon is added to the iron ore. This carbon typically comes from coking coal, which undergoes high-temperature processing. Other elements like chromium, manganese, nickel, or molybdenum are also added to the steel to enhance its strength and other critical properties. Every year, more than 15 million tons of steel are used worldwide for railway tracks. This represents a significant portion of global steel production, and demand continues to grow due to infrastructure expansion and the need to replace worn-out tracks. After extraction and initial processing, the raw materials are transported to steel mills. Rail and maritime transport are commonly used, especially for long distances, since ore is often mined in remote areas. Thus, steel production for rails involves combining various materials sourced from different parts of the world, with the extraction and processing stages relying on complex machinery and a multi-step refining process. The production of railway tracks begins in the steelmaking facility, where iron ore and other components are melted in specialized electric or blast furnaces to create molten steel. Carbon and alloying elements are then added to the steel to enhance its strength. Once the desired composition is achieved, the metal is maintained at a high temperature to ensure uniformity. The molten steel is poured into large molds, forming slabs, rectangular blocks of steel that will eventually be shaped into rails. After cooling, the slabs are transported to the rolling mill for further processing. A rolling mill is a massive machine that shapes steel slabs into the desired form and size for rails. The slabs pass through a series of rollers, which gradually reduce their thickness and form the railhead, web, and base. The rails are rolled at temperatures exceeding 1,832 degrees Fahrenheit, making the metal more pliable. To increase the hardness and wear resistance of the rails, a heat treatment process is applied. The rails pass through cooling chambers, where the temperature is gradually reduced, minimizing internal stress in the metal. Typically, 1 foot of rail weighs about 45 to 55 pounds, meaning a standard rail weighs approximately 3,858 pounds. A large steel mill can produce around 3,500 feet of rails per shift, roughly 10,000 feet per day. Once the rails are finished, they undergo thorough inspections for defects such as cracks, surface irregularities, or other damage. Specialized ultrasonic and X-ray techniques are used to ensure quality. After inspection, the rails are cut to standard lengths of approximately 1,000 inches, and their ends are machined for easier connection during installation. Once manufactured, the rails are transported to construction or repair sites. Trains specially designed for carrying long rails are typically used for this purpose. Freight cars secure the rails tightly to prevent any movement during transit. Laying railroad tracks is a complex process that requires the use of specialized machinery. First, the ballast, which serves as the foundation for the ties and rails, is leveled and compacted along the railway bed. This ballast is crucial for the stability of the tracks and for proper drainage. Ballast spreaders evenly distribute the crushed stone, creating a stable layer on which the ties and rails will be laid. Automatic tie-laying machines then place wooden or concrete ties on the prepared ballast base, ensuring they are spaced precisely. These machines are equipped with sensors to maintain an exact distance between the ties. which is essential for the stability of the future track. Railroad rails can last up to 30 years or more, depending on the volume of traffic and environmental conditions. However, on high-traffic routes, such as those used for freight trains, rails may wear out more quickly and require replacement every 10 to 15 years. Next, the rail laying machines take over. And oh my goodness, what a mesmerizing sight it is. When we think of rails, we usually picture something as rigid as stone. Yet during the laying process, they seem to bend under the influence of the machines, almost like rubber bands. In reality, this is due to the immense forces acting on them. When rails are first rolled out, they're heated to extremely high temperatures to make the steel more malleable and easier to shape. During installation, rails are sometimes reheated to prevent future thermal expansion, which gives them that seemingly softer, more pliable appearance. Specialized machines carefully lift, align, and position these long sections of rail as though they're weightless and not the solid, unyielding steel we know them to be. It's all thanks to precise manipulation and the illusion of flexibility, which cleverly conceals the incredible strength of the steel. This is one of those fascinating railway magic tricks, where raw power and advanced technology combine to create a spectacle that's as captivating as it is impressive. Workers then join the rails using specialized bolted or welded joints. Thermite welding or electric welding equipment is employed to create a seamless rail line, ensuring a smooth ride for trains. It's remarkable how much effort goes into making it possible for me to visit my favorite grandma, or for any office worker to commute to their job. To secure the rails to the ties, special fasteners are used to clamp them firmly in place. This ensures stability and prevents the rails from shifting under the weight of passing trains. Rails have the ability to freely expand and contract by a few millimeters for every 10 yards, depending on the temperature. As a result, when laying tracks, engineers take average annual temperatures into account. In some cases, the rails are even heated to a specific temperature during installation to minimize the effects of thermal expansion. Automatic fastening machines quickly install bolts or clips to connect the rails to the ties, significantly speeding up the process. Once the rails and ties are in place, specialized machines align the track by lifting or lowering the ties and adjusting the ballast beneath them. Thanks to laser sensors and computer control, these machines ensure precise track alignment, which is critical for safety. Other machines tamp the ballast, crushed stone, around the ties, providing a solid foundation. This reduces the risk of track shifting and enhances its resistance to vibrations. These machines are equipped with special tamping arms that dig deep into the ballast and compact it firmly around the ties. Rails are often made using a significant percentage of recycled steel, as steel retains its properties well during reuse. This helps reduce the need for new ore extraction and lowers the carbon footprint, contributing to a more sustainable production process. Do you know how many servings of instant ramen are consumed worldwide each year? Over 100 billion, and in the United States alone, up to 5 billion. In this video, I'll show you how simple dough is transformed into noodles that save students and office workers from hunger in just 3 minutes. We'll talk about the different types of noodles, the production process, and how all those amazing flavors are added. And of course, we'll dive into what it means to get invited out for ramen in various Asian countries. The production of instant ramen, yes, that iconic quick cooking noodle, is a highly technological process involving specialized machines for mixing, shaping the noodles, quick cooking, and packaging. I've seen how noodles begin their journey, starting with dough preparation. The base for these noodles consists of flour, water, salt, and an alkaline solution called kansui, which gives ramen its signature springy texture and yellowish hue. The type of flour used in instant ramen is crucial. High gluten flour, typically made from hard wheat, is the standard. The high gluten content ensures the dough is elastic and strong, which is essential for the noodle's texture. Sometimes, the flour is further treated or blended with small amounts of potato or cornstarch to enhance the noodle's elasticity and firmness after cooking. It's pure culinary magic. By the way, outside of Asia, Instant ramen is one of the most popular ready-to-eat foods in the world, especially among students and travelers. The ingredient delivery process is typically automated. Flour, water, salt, and kansui are fed into the mixer from large containers through specialized dispensing systems. This setup allows for precise control over the proportions of each ingredient in every batch of dough. Sensors are commonly used to measure the exact quantities, and once everything is loaded, the machine automatically starts the mixing process. I was amazed at how powerful the mixing blades are in these machines. These blades ensure intense and uniform mixing of the dough to prevent lumps and achieve the ideal texture. They move in different directions and at varying speeds, which helps to evenly hydrate the dough and enhance its elasticity, especially with the addition of kansui, which gives the noodles their distinct structure. The first instant ramen was invented in Japan in 1958, and at the time, it was considered a luxury item rather than a quick meal option. After mixing, the dough is automatically transferred to the resting section, a crucial step where the gluten develops to the desired level, giving the dough a uniform texture. The resting machine is equipped with several layers of conveyor belts stacked one above the other. The dough is placed on the top conveyor, which moves slowly, allowing the dough to rest while gradually advancing. The conveyors operate at a slow pace to provide the dough with the necessary resting time. As the dough travels through all the levels of the machine, it rests for 10 to 30 minutes, depending on the recipe and the type of noodle being produced. This resting period allows the gluten to stabilize, making the dough more elastic, resilient, and better able to hold its shape after cutting. The machine maintains optimal humidity and temperature to prevent the dough from drying out or losing its essential qualities. Some machines are even equipped with specialized steam humidifiers to ensure the dough stays properly hydrated throughout the process. Once the dough has completed its resting phase, it is automatically fed out of the machine and into the rolling section for noodle shaping. The dough enters a machine equipped with a series of rolling rollers. These rollers gradually reduce the dough's thickness with each pass until it becomes thin, typically less than an inch thick. Each pair of rollers rotates at a specific speed to ensure uniform thickness without overstretching the dough. Modern factories, thanks to automation, can produce up to 1 million servings of instant ramen per day, making the process both highly efficient and consistent. Once the dough reaches the desired thickness, it moves on to the cutting stage. The machine is equipped with a set of sharp blades that slice the dough into strips of a specific width. The width varies depending on the type of noodle, ranging from thin to wide. These freshly cut strips automatically form long noodles, ready for the next step in the process. What fascinated me the most was how they make the ramen wavy. I finally saw that the shaping machines are equipped with special vibrating mechanisms or profiled rollers. During the cutting process, these mechanisms vibrate, causing the noodles to curl into small waves. Amazing, right? The entire machine vibrates, and the noodles naturally take on that classic wavy shape. Truly incredible. Wavy noodles not only hold their shape better in packaging, but also absorb broth more quickly once hot water is added. It's a beautiful process. It's no wonder Japan has museums dedicated to the history of instant ramen, where visitors can learn about its evolution and even create their own unique serving. In the final stage, the shaping machine divides the noodles into individual portions. Special blades cut the noodle strips to a specific length, ensuring they fit neatly into the packaging. The portioned and shaped noodle blocks are then sent onto a conveyor belt for the next step, either pre-cooking or drying. This automated process helps maintain the integrity and uniformity of each portion. Defect control at this stage is also fully automated. I was fascinated to learn that the machines are equipped with sensors and computer systems to monitor quality, ensuring consistent thickness, width, and length of each noodle strip, while also detecting potential defects. Next, the noodles need to be cooked, and I was amazed to see how they are passed through powerful steamers, where they are cooked for several minutes. This step is crucial for preserving the texture and flavor. After cooking, the noodles are fried in hot oil. Special machines equipped with high-temperature vats ensure even frying. This method gives the noodles their crispiness, and makes them suitable for quick preparation. Now I know that there are more diet-friendly types of ramen, and the difference lies in this stage of production. To avoid adding oil, some noodles are dried using hot air instead. Specialized drying chambers circulate hot air to evaporate moisture. After drying, the noodles are ready for packaging. In instant ramen production, fully automated packaging lines are used. Personally, this is one of my favorite stages to watch during factory tours, aside from the tasting, of course. The machines cut or shape the noodles into compact blocks that fit neatly into the packaging. Each noodle block is placed in a waterproof bag or container. At the same time, packets of seasonings and flavorings are added to enhance the taste when prepared. Naturally, every package includes a small packet of concentrated spices and broth, either in powder or paste form. These may contain soy sauce, meat broth, dried vegetables, and various spices. This ensures that instant ramen has a rich, flavorful taste once water is added. Every stage of instant ramen production undergoes quality control to ensure a safe and consistent product. This process includes checking the quality of the noodles, moisture levels, and the weight of each block. Specialized detectors also scan for the presence of any foreign objects in the finished products. Once packaged, the instant ramen packs are placed into boxes and sent to storage facilities. The product has a long shelf life thanks to the dried or fried noodles and airtight packaging. Storage conditions must maintain low humidity and a stable temperature to preserve product quality. In the United States, instant ramen is incredibly popular. Every year, approximately 4 to 5 billion portions are consumed, placing the US in the top 10 countries by consumption volume. While the per capita consumption is much lower than in countries like South Korea, Japan, or China, Americans still enjoy this product for its convenience, quick preparation, and affordability. If you were to stretch the noodles from a single packet into one continuous line, it would measure about 3 yards. And I haven't been able to stop thinking about that for days. Guess what I'll be doing today? As for an invitation to eat ramen in Asian countries, it's their equivalent of asking someone to Netflix and chill after a date. Every day, over 100,000 bottles of ranch dressing make their way to store shelves. But did you know that producing this requires 22,000 pounds of dairy products per shift, with pasteurization occurring at 161 degrees Fahrenheit for 15 seconds? It's more than just a sauce. It's an entire industry. Let's break down how the world's most popular dip is made. The main ingredients of ranch dressing are dairy products, vegetable oils for mayonnaise, and fresh or dried spices. Every batch of raw materials that arrives at the production facility undergoes lab testing to ensure purity, freshness, and compliance with chemical and physical standards. Dairy products are tested for fat content, which should be around 10 to 20% to achieve the desired consistency, and for bacterial purity. Spices are analyzed for their essential oil content, which impacts the flavor. Manufacturers often use enterprise resource planning systems to track and control the origin of each ingredient. This ensures full transparency. For instance, if a batch with quality issues is identified, the system can trace the source and exclude it from future shipments. The production line is equipped with sensors to verify ingredient identity, and every batch is scanned and automatically inspected. Companies purchase raw materials in large volumes, such as 10 to 20 tons of buttermilk per month, ensuring a steady supply for production. Ingredients that do not meet quality standards are automatically rejected during procurement through automated systems that filter batches based on specific parameters. The system calculates the exact amount of ingredients needed based on the planned production volume. Software tracks the usage of each ingredient, helping to prevent overuse. Additionally, the automated purchasing system allows manufacturers to secure bulk discounts, reducing overall ingredient costs by 3 to 5%. The first step in the process is the receipt of raw materials, where both speed and precision in quality control are crucial. For instance, a typical ranch dressing production line processes up to 22,000 pounds of dairy products and up to 11,000 pounds of other components, like mayonnaise, spices, and oils in a single shift. ERP systems automatically log every batch of raw materials that arrives at the facility. Each batch of buttermilk is identified using a QR code or RFID tag, which contains detailed information about its origin, expiration dates, and certifications. Once received, the raw materials are sent to the lab for rapid testing. A milk analyzer measures fat, protein, and moisture content in under 5 minutes, with an accuracy of 0.1%. To check for bacterial contaminants like E. coli or Salmonella, modern PCR, polymerase chain reaction, analysis systems are used, delivering results in just 2 to 3 hours. Previously, this kind of testing could take several days, but automated systems now dramatically reduce the time, ensuring quick and reliable quality control. Impressive! Most ingredients undergo mandatory cleaning and sterilization before mixing to remove impurities and eliminate microbes. Fresh spices like garlic and onions are cleaned using infrared sorting machines, which detect and remove spoiled or rotten items with an accuracy of up to 98%. Other spices also go through infrared or steam cleaning processes. Buttermilk and sour cream are pasteurized to kill any pathogenic bacteria, ensuring they meet the highest safety standards. You've heard about my love for other foods, so now it's time to reveal my secret weapon in the culinary world. Let's just say, cooking isn't exactly my strong suit. I'm one of those people who can turn a simple Sunday barbecue into a game of find 1,001 ways to fix this terrible flavor. Take my burgers, for example. Not only did I oversalt the patties, but I also added super spicy pickles for a little kick. It was such a disaster that I was ready to grill a whole new batch. But then, I decided to give ranch a try, and it worked. Turns out, this sauce is a miracle worker. It tames the saltiness and adds a creamy, mellow flavor that even saves my culinary mishaps. Alright, I think it's time to get back on track. The best part is just about to begin. Once all the ingredients are prepared, they are automatically fed into the mixers. Conveyor lines and automated pipes are used to transport the ingredients, ensuring that each component reaches the mixer without coming into contact with air or any foreign substances. For the production of ranch dressing, specialized high-speed mixers are utilized, capable of handling large volumes of ingredients in a short amount of time. For instance, mixers equipped with spiral blades can process up to 3,000 pounds in one batch, ensuring the even distribution of all components. These mixers are also fitted with sensors to monitor the temperature throughout the process. The temperature is maintained at 36 degrees Fahrenheit, which helps preserve the product's flavor and texture. If the temperature rises, an automatic cooling system activates to maintain optimal conditions. Depending on the recipe, the mixing duration can vary from 10 to 20 minutes. The system automatically adjusts the blade rotation speed, direction, and timing for each ingredient. For example, spices are added after the first minute of mixing to prevent them from settling. To ensure even distribution of the components, sensors measure the sauce's density and viscosity every 30 seconds. Ranch dressing must be thick enough to remain stable during storage. An integrated analyzer checks the viscosity of each batch, with an accuracy of up to 0.1%. If necessary, the software can adjust the mixing time or intensity. Additionally, the potential of hydrogen pH level is measured, as acidity is crucial for both the flavor and stability of the product. Ranch dressing typically has a potential of hydrogen pH range between 4.2 and 4.4 to achieve the optimal balance of taste and preservation. The system automatically monitors acidity and can add pH regulators if deviations occur. Before pasteurization begins, ranch dressing is transferred from the mixing stage to specialized pasteurization tanks through sealed pipes, minimizing contact with air and preventing contamination. These tanks are equipped with automatic sensors that monitor the incoming volume of sauce and calculate the optimal amount for pasteurization. The pasteurization process for ranch dressing requires strict control of temperature and timing to effectively eliminate pathogenic microorganisms while preserving the product's flavor. Typically, the high-temperature short-time method is used, where the sauce is heated to 161 degrees Fahrenheit and held at that temperature for 15 to 20 seconds. The primary equipment used for pasteurization is a plate heat exchanger, which enables rapid heating and cooling of the sauce through thin metal plates. Thanks to the large surface area of the metal plates, heat is transferred very quickly, minimizing the time the sauce spends at high temperatures. This allows for a processing speed of approximately 800 gallons per hour, a highly efficient rate for industrial sauce production. After pasteurization, it is crucial to cool the sauce quickly to prevent bacterial growth and preserve its flavor. This is achieved in the cooling sections of the heat exchanger. The sauce is cooled to below 40 degrees Fahrenheit within seconds. Rapid cooling inhibits bacterial growth and helps maintain the natural taste of the ingredients. Before packaging begins, the sauce is transferred from the pasteurization stage to specialized intermediate storage tanks. Each tank holds between 500 and 1,000 gallons and maintains the sauce at the required temperature. Depending on the order, the sauce is packaged into bottles, pouches, or containers of various sizes. The production line is equipped with multifunctional dispensers that ensure precise portioning. Depending on volume, the line can fill up to 500 bottles or containers per minute. Every package filled with sauce undergoes an automatic sealing process to ensure airtight closure. For bottles, specialized capping machines are used, capable of screwing on up to 300 caps per minute. For pouch packaging, heat sealing machines create secure, airtight seams. Temperature and pressure are automatically monitored to ensure the packaging is strong and durable. The production volume of French fries reaches 4 or even 5,000 tons per day. In the massive factories of the United States, the process of making French fries resembles a coordinated symphony of machinery, engineering expertise, and quality control. Production at facilities like McCain, Lamb Weston, or Simplot involves large-scale operations that make it possible to deliver tons of crispy fries to fast food restaurants, supermarkets, and food service establishments worldwide. Let's take a closer look at how this process works. Here we go. To make a delicious product, you need the best raw materials. Special varieties of potatoes, such as Russet Burbank or Innovator, are used for French fries. These varieties have a high starch content, ensuring the right texture and flavor. Factories receive millions of tons of potatoes from farming operations. A single large factory can process up to 1 million tons of potatoes annually. The potatoes are delivered by trucks that maintain optimal temperatures to prevent spoilage. Each truck typically carries between 20 and 30 tons of raw potatoes. To preserve quality, transportation happens immediately after harvest. At the factory, the truck backs onto a specialized platform that tilts the truck bed, allowing the potatoes to slide into a receiving hopper via gravity. Unloading a single truck takes less than 5 minutes. During peak season, a factory can handle up to 500 trucks per day. As the potatoes are unloaded, they undergo an initial inspection. Magnetic and mechanical separators are used to remove any metal or stone debris that might have been mixed in with the potatoes during harvesting. In the first stage, I observed how potatoes are washed in large automated drums using high-pressure water. A conveyor system evenly distributes the potatoes onto washing and sorting lines. Factories typically have their own wells or are connected to local water supply systems. Before use, the water undergoes multiple purification steps, including mechanical filtration, to eliminate impurities. Most factories recycle up to 90% of their water, significantly reducing costs. Water is delivered to the conveyor washing systems via powerful pumps that generate the necessary pressure for effective cleaning. Spray nozzles evenly distribute water over the potatoes as they move along the conveyor. The potatoes pass through rotating drums, where high-pressure water removes most of the dirt. Some factories use water baths with air bubbles for a gentler cleaning process, ensuring that dirt residues are removed without damaging the potatoes. This process thoroughly cleans the potatoes, removing soil, dirt, stones, and debris. The water used for washing is collected in reservoirs, where it is filtered to remove solid particles. Once purified, the water is recirculated back into the system. This setup saves thousands of gallons every day. To peel potatoes, special mechanical devices are used to leave only the clean, soft flesh. First, the potatoes pass through abrasive drums with walls coated in rough materials. As the drum rotates, the skin is scraped off, and the clean potatoes move along the line. This method is highly effective for large volumes, processing up to 20 tons of potatoes per hour. Next, the potatoes are placed in high-pressure chambers, where steam is introduced at a temperature of about 131 degrees Fahrenheit. Under pressure, the steam penetrates the skin, softening it. Afterward, the temperature difference and a strong airflow separate the skin from the potato. Following this initial cleaning, the potatoes are processed on polishing rollers to achieve a perfectly smooth surface. This step removes any tiny bits of skin or other imperfections. Why? Why didn't I have one of these chambers as a kid? I used to hate peeling potatoes. It could have been so simple. Just whoosh, and the skin would be gone. Life is unfair. Next, the potatoes pass through high-speed cutting machines that slice them into the desired size and shape. There are plenty of options: classic fries, thick, home-style cuts, crinkle cuts, or even spirals. Personally, my favorite is the classic fry. What about you? These machines can cut more than 14 pounds of potatoes per hour. Did you know that several countries claim the origins of French fries? However, it was America that truly popularized them, spreading their deliciousness worldwide. The next process is called blanching. This step is critically important for achieving the perfect color, texture, and flavor. Sliced potatoes are immersed in hot water, approximately 86 degrees Fahrenheit, for 1 to 2 minutes. This process removes excess starch, enhances the color, and helps prevent the formation of harmful compounds during frying. After blanching, the potatoes are passed through drying systems that remove excess moisture. As I have been informed, this ensures a uniform texture and crispy crust. First, the potatoes are loaded onto a conveyor. Excess water initially drains naturally through openings in the conveyor. The potatoes are then transported into a drying chamber, where they are exposed to a powerful stream of hot air. The air temperature must not exceed 60 degrees Fahrenheit to avoid damaging the structure of the potatoes. Depending on the size of the slices, for standard thickness French fries, drying takes no more than 30 seconds. At this factory, the dryer can process up to 22,000 pounds of potatoes per hour. Potatoes are fried in vegetable oil, which can be corn oil, canola oil, or sunflower oil. The fryer temperature reaches 176 degrees Fahrenheit. The potatoes are fed into the fryer via a conveyor belt. On a side note, I'll let you in on a secret. My girlfriend seems to take baths at the same hellishly hot temperature as these poor potatoes, worn out by all the processing. Before frying, automated systems inspect the product once more to remove any overly small pieces that might burn. The calibrated potato pieces destined for frying are evenly distributed on the conveyor belt to prevent them from sticking together during the frying process. The potatoes move through the oil on the conveyor, submerging evenly to ensure consistent frying. During frying, the oil is continuously filtered to remove small potato particles and prevent overheating or oxidation. To avoid burns or the formation of bubbles on the surface of the product, the potatoes are gradually lifted out of the hot oil, ensuring a smooth temperature transition. The total immersion time is approximately 1 minute, just enough to create a light, crispy outer layer. After frying, the potatoes pass through tunnels with streams of cold air, which helps preserve the product's freshness and quality. Cooling French fries after frying is a crucial step in the production process, as it prepares the product for subsequent stages, such as freezing or packaging. The entire process is carried out quickly and meticulously. Cooling helps maintain the fries' crispiness and minimizes internal softening. Additionally, it prevents the formation of excess condensation, which could compromise quality during freezing. After frying, the potatoes are loaded onto specialized conveyors equipped with air tunnels. Powerful fans circulate cooled air through these tunnels, and their speed is adjustable to avoid damaging the fries. For uniform cooling, the potato pieces are continuously stirred or flipped on the conveyor belt. A single cooling tunnel can process up to 11,000 pounds of potatoes per hour. The potatoes are weighed and automatically packaged into bags of various sizes. One production line can package up to 150 bags per minute. Impressive speed, isn't it? The cooled or frozen fries are transferred onto specialized conveyor belts. Vibrating feeders evenly distribute the pieces along the belt, ensuring precise weighing. The scales analyze the fries in real time and select the optimal combination to achieve the target weight. After weighing, the potatoes move to packaging machines, where the bags are formed. There are generally two types of packaging: soft polyethylene bags for retail sales, and large paper or plastic sacks for restaurants. The machines seal the bags using heat-sealed seams, ensuring airtight packaging that protects the product from oxidation. Some bags are filled with nitrogen to preserve the fries' quality for longer periods. Once sealed, labels are applied to the packages, displaying product information such as weight, ingredients, production date, and expiration date. The finished product is stored in refrigerated warehouses, where a constant temperature of -8 degrees Fahrenheit is maintained. A single package of McDonald's French fries can pass through the entire factory process in under 60 minutes. Annually, more than 11 million tons of French fries are produced worldwide, with the majority manufactured in the United States. This entire process is a marvel of engineering, enabling billions of people to enjoy delicious and high-quality French fries. Hey bro! Today, we're diving headfirst into the wild world of money, straight to the US Bureau of Engraving and Printing. That's the spot where real-deal dollars are born, the ones that end up in people's pockets and keep the global economy humming. But listen, these aren't just some random pieces of paper with numbers slapped on them. Every bill is a legit masterpiece, packed with cutting-edge tech. We're about to uncover the secrets behind that one-of-a-kind paper, the mind-blowing microscopic details, and the top-tier security features that make the dollar untouchable. You ready? Let's roll. This is gonna be epic. First off, forget about regular paper. Dollars are printed on some next-level stuff made by Crane and Company. This isn't your basic white office paper. It's a cotton-linen blend with a unique texture that's totally different from the usual. That's why dollars have that crisp crinkle and last way longer. The material is 75% cotton and 25% linen, with tiny colored fibers woven in that you can only spot under a microscope. Plus, the paper is packed with watermarks and embedded security threads, making it nearly impossible to fake. This paper gets delivered in massive rolls, each one guarded like it's gold. And boom, that's step one in the battle against counterfeiters. Now we're stepping into the engraving department, the place where the magic happens and the main design for each bill is born. This is where artists, known as engravers, carve out the intricate designs and portraits by hand on metal plates with jaw-dropping precision. Take those iconic presidential portraits, like George Washington on the $1 bill or Benjamin Franklin on the $100 bill. They're painstakingly recreated from photographs. And those lines that look straight? They're actually made up of microscopic details. That's another layer of protection. No regular printers pulling that off. Feeling a little outclassed? Don't sweat it. This stuff is straight up genius. Next up, we're heading into the heart of the factory, where the real magic of printing goes down. Check out those massive printing machines using the intaglio technique. That's fancy talk for deep engraving. Here's how it works. The metal plates made by the engravers are coated with ink, and then the excess is wiped off, leaving the ink only in the engraved grooves. The paper is then pressed onto the plate under insane pressure, transferring the ink onto it. Thanks to intaglio printing, certain features on the bills, like the portraits, have a raised texture you can actually feel. How cool is that touchable detail? This process happens multiple times because dollars are printed in layers. First comes the black ink, then green, and finally, other security features are added. Every year, they crank out about 7 billion bills here, with 95% replacing old or worn-out cash. Oh, and the ink? It's so tough that even if you bury a dollar bill for 20 years, you'd still be able to recognize it. In today's world, where counterfeiters are getting slicker by the day, money has to level up with serious protection. For instance, there's microprinting, tiny text you can only see with a magnifying glass, added around portraits or borders of bills. It's so small and detailed, it's practically impossible to fake. Then there are those special security threads embedded in the paper. Under ultraviolet light, these threads glow in different colors depending on the bill's value. For example, $5 glow blue, while $100 shine pink. And let's not forget the $100 bill. It's loaded with high-tech features like 3D holograms that shift and change depending on the angle you look at them. How's that for next-level security? Next stop, the offset printing section. This is where those background images, like the green and golden hues you see on dollars, are added. It's the second line of defense. Intricate patterns and color gradients that are almost impossible to replicate with basic tools. Rolls of future cash spin on cylinders, feeding into the printing machine. Once the ink is applied, the rolls are cut into sheets of the perfect size. Fun fact, a dollar bill lasts on average 5 to 8 years before it's retired. On the back of the $1 bill, you've got the pyramid symbolizing strength and durability, while the all-seeing eye represents divine protection. Pretty wild, right? Let's keep this tour moving. Bro, now we're in the room where dollars get their names. This is where each bill gets its unique serial number, printed in either black or green ink. It's basically the ID code for every single banknote. The next step? Stamping the Federal Reserve seal. These seals show which of the 12 Federal Reserve banks issued the note. This whole process happens on high-speed printing machines that churn out thousands of bills per minute. And get this, the printing conditions are no joke. The machines apply 80 tons of pressure, and the wax-based ink is literally baked into the paper under high heat. The ink is specially designed to resist wear and tear, even something as wild as going through the wash. Oh, and here's a crazy stat. The total value of all cash dollars in circulation is over 2 trillion. How's that for some money talk? Before dollars leave the factory, they go through some hardcore quality control. High-tech scanners check every single bill for defects. Blurry ink, damaged paper, or misaligned designs. If there's any mistake, the bill is pulled out of circulation immediately. The ones that pass, they're neatly packed into stacks of 100 bills. The final step is packing the money. These stacks are loaded into special containers and shipped off to Federal Reserve banks. From there, they make their way to commercial banks and eventually into people's hands. The whole transportation process is locked down tight, with heavy security. We're talking millions of dollars here after all. When a bill is declared too worn out, it gets destroyed. Don't get teary-eyed, bro. Let's check out how it happens. Worn-out banknotes are tossed into industrial shredders that chop them into tiny bits. According to the Federal Reserve, around 5 billion bills are shredded every year, mostly $1 and $5 notes, since they take the hardest beating from daily use. But shredded cash doesn't just get thrown away. The Federal Reserve is big on keeping things eco-friendly, so they find ways to repurpose the materials. Here's a funny story. One time in Texas, some clueless criminal broke into a Federal Reserve facility, thinking he'd hit the motherlode. Instead of stacks of cash, though, he walked off with a giant bag of shredded money. Thinking he'd scored big, he dragged his loot home. Spoiler alert, shredded cash is worth zilch. The guy got caught within a day. Tough luck for him, but at least we got a good laugh out of it. In some states, shredded bills are pressed into dense briquettes that are used as fuel for energy production. Pretty cool, right? This process replaces wood or coal, cutting down on environmental harm. In areas with the right tech, the shredded cash can even be turned into compost, since cotton linen paper is biodegradable. Yeah, money literally gets buried in the ground. A portion of the shredded banknotes is also repurposed into souvenirs. For example, they're packed into clear balls or boxes and sold to tourists at gift shops in the Bureau of Engraving and Printing. It's a unique way to hold a piece of money history in your hand. So, how about it, bro? Want to snag a chunk of chopped up cash for your shelf? Destroying large sums of cash is a whole other level of operation. When entire series of banknotes are pulled from circulation due to design updates or new security features, the disposal process gets even more intense. The old bills are transported in armored vehicles under strict surveillance, and every step of the destruction process is carefully documented to make sure not a single bill ends up in the wrong hands. This massive operation is actually cost-effective in the long run. For instance, according to the Federal Reserve, the cost of destroying a single bill is just 0.03 cents, thanks to automation. Every day, up to 200 tons of banknotes are shredded across the US. Even the machines used to destroy bills are guarded as tightly as the money still in circulation. It's a big deal, but hey, with that kind of precision, counterfeiters don't stand a chance. When it comes to durability, $1 bills last about 6.5 years on average, while $100 bills can stay in circulation for up to 22 years since they're handled less often. Not bad, bro, especially when you compare it to the lifespan of large denomination euro bills, which is only about 5 years. So, how do they decide when it's time to retire a bill? That's where the Federal Reserve's specialized machines come in. These machines assess the condition of banknotes and flag the ones too worn for circulation. But here's the kicker: the actual disposal doesn't happen at the same place as the printing. The Bureau of Engraving and Printing only destroys defective bills that pop up during production. For example, if the ink isn't applied evenly or the paper gets damaged, those bills are immediately shredded. Quality control on point, right? A few years back, a group of criminals in the US decided to rob an armored truck carrying cash. They planned the heist down to the last detail, but they picked the wrong moment to strike. Instead of shiny, fresh bills, the truck was hauling worn-out banknotes headed for destruction. The plan might have seemed genius at first, but the payoff? Practically worthless. Talk about a major flop. Then there's the classic case of the thief who tried to snatch some cash from a bank. In his rush to get out, he grabbed a bag full of bills, completely clueless that it was rigged with die packs. The second he stepped out of the bank, boom! The capsule exploded, covering both the cash and the crook in bright, unmistakable dye. Those bills became totally useless, and the mastermind left a literal trail of evidence straight to where the cops nabbed him. Honestly, I bet that trail wasn't just bright red or purple. There was probably a little brown in the mix too. Not that the press would mention that part. Here we are, standing at the entrance of a massive cornflakes factory. Did you know that around 4 billion pounds of cornflakes are made worldwide every year? Impressive, right? You ready? Let's go. I'll walk you through everything step by step, from the very beginning all the way to how these crunchy, delicious flakes end up on your breakfast table. It all starts in the cornfields. For cornflakes, a specific type of corn is used, yellow dent corn. This variety isn't like the sweet corn we're used to eating boiled or grilled. It's starchier and contains less sugar, making it perfect for processing. The corn is harvested using massive combines that literally slice through the fields, stripping the cobs and separating the kernels. From there, it's sent to the factory. Before transportation, the corn is carefully dried to reduce moisture and preserve its quality during transit. At the factory, the kernels undergo hundreds of tests. They're checked for size, density, moisture levels, and even color. Every detail matters to create perfectly uniform and crispy flakes. And when it comes to cornflakes, the most iconic brand is still Kellogg's, which first introduced them way back in 1894. Cornflakes, like many culinary inventions, were born out of a mix of chance and experimentation. They were created by the Kellogg brothers, John Harvey Kellogg and his younger brother, Will Keith Kellogg, in the late 19th century. John Harvey Kellogg was a doctor and the director of a sanitarium in Battle Creek, Michigan, USA. His sanitarium followed strict principles of healthy living, offering patients a plant-based diet, physical exercise, and even some rather radical treatments, like hydrotherapy. One of John's main goals was to develop healthy and easy-to-digest food for his patients. Will Keith Kellogg, his brother, worked alongside him at the sanitarium, handling administrative tasks and helping bring his ideas to life. In 1894, John and Will were experimenting with different ways to process grains to make them easier to digest. One day, they cooked a batch of wheat dough, but accidentally left it out to dry for too long. By the time they returned, the dough had become overly dry and brittle. Curious, they decided to run it through rollers to see what would happen. To their surprise, the result was thin flakes, which they toasted to make crispy. The patients at the sanitarium loved them. Later, the brothers decided to try experimenting with corn, as it was cheaper, more widely available, and delivered even better results. And just like that, cornflakes were born. After the success of their flakes, Will Keith Kellogg saw massive business potential and wanted to sell them on a larger scale. However, John Harvey Kellogg disagreed. He viewed them solely as dietary food for patients. In 1906, Will founded the Kellogg's Company, which remains the world's largest producer of cornflakes to this day. The production scale has grown so much that Kellogg's now uses over 1.5 billion pounds of corn every year. Cornflakes became a massive hit in the US, especially among women who loved them as a quick and easy breakfast option. The original recipe was simple, just corn, salt, and a little sugar. Today's versions come in dozens of flavors and include all kinds of additional ingredients. Now here we are inside the production floor. Huge silos are filled with corn, which is gradually fed into the first stage, cleaning. Specialized machines remove debris, stones, leftover cobs, and husks. Next, the corn goes through a magnetic separator. You might be wondering, why a magnet? It's to ensure no metal fragments from harvesting or transport make it through. Once the corn is thoroughly cleaned, it's sent to giant tanks filled with hot water. Here, it cooks for several hours at around 212 degrees Fahrenheit. This softens the kernels and allows them to absorb moisture, preparing them for the next stages of processing. After boiling, the corn is moved into machines that separate the germ and the hull from the kernel. The germ, the part of the grain that's packed with oil, is removed so the flakes don't turn out too greasy. Once the kernel is cleaned, it's ready for the next step, roller processing. And here's where things get really exciting. The cleaned corn kernels are poured into specialized steel rollers that, under immense pressure, flatten each kernel into a thin sheet. These rollers spin at incredible speeds, and the entire process happens almost instantly. Watching it in real time feels like magic. Corn literally transforms into flakes right before your eyes. The flattened kernels now resemble thin, golden discs. But hold on, they're not quite the flakes you're used to eating just yet. Now we're getting to the massive ovens. This is where the flakes are dried and toasted at around 482 degrees Fahrenheit. It's here that they develop that perfect, crispy texture and beautiful golden color. Imagine the smell in this room. It's like popcorn, but sweeter. At this stage, a touch of sugar, salt, or even honey is added to the flakes, depending on the recipe. For glazed flakes, they're coated with a thin layer of sugar syrup that caramelizes right in the oven. How many crunchy flakes could you eat? Fun fact, there's even a championship for speed-eating cornflakes, and the record stands at 16 ounces in just 1 minute. Crazy, right? Now watch as countless hot, crispy flakes roll off the conveyor belt. But not all of them make it into the boxes, only those that pass quality control. Special machines check their shape, thickness, and even the sound they make when they break. Seriously, that's a real quality measure. Once the flakes are ready, they're cooled and packed into bags. The machines automatically weigh each portion, seal it in foil-lined bags to keep it fresh, and place it into cardboard boxes. It takes about 3.5 ounces of corn to produce 1 box of flakes, but growing that amount of corn requires 5 gallons of water. Here's a fun throwback. In the 1980s, a British company tried selling cornflakes in cans, like soup, but the idea flopped because customers thought it looked too weird. Almost 100% of cornflake boxes are made from recycled cardboard, and the printing is done with soy-based ink. Here we are, standing next to the warehouse filled with ready-to-go products. Just imagine, these boxes of cornflakes are about to head out to every corner of the globe. They'll be breakfast for kids in the United States, snacks for students in Europe, or even a key ingredient in desserts across Asia. Fun fact, cornflakes were actually invented in the United States, but today, they're a hit in over 180 countries worldwide. Modern factories take eco-friendliness to the next level. Leftover corn from processing gets repurposed as livestock feed, and the cardboard boxes? They're made from recycled materials. Oh, and here's a surprising twist. In some farming communities, cornflakes are actually used as cattle feed. Farmers discovered that cows love this stuff. Cornflakes have even made it to space. They were included in the diets of American astronauts during NASA missions. Every year, more than 6 billion servings of cornflakes are consumed worldwide. That's enough to feed the entire population of Earth breakfast for 3 weeks straight. And here's something crazy. Listen closely. If you place a magnet near cornflakes, they might actually move toward it. Why? Because cornflakes are fortified with iron, an essential nutrient for human health. Have you tried it yourself? Drop a comment and let us know what happened. You have no idea what's behind every sweet bar of Snickers. Today, you'll step into the secret workshops, see robotic machines, and discover genius engineering solutions that bring your favorite candy bar to life. We'll uncover shocking facts about nougat, caramel, and peanuts, and show you how that crunchy chocolate layer is born. Stick around till the end, and you'll never look at a Snickers the same way again. Get ready for an explosion of flavor and technology. Snickers was created in 1930 by Mars Incorporated. The bar was named after the Mars family's favorite horse. Since then, Snickers has become one of the world's most popular chocolate treats, sold in more than 80 countries. But making Snickers isn't just about mixing ingredients. It's a precise, high-tech, and incredibly fascinating process. The first step in making a Snickers bar is preparing the ingredients. The main components are nougat, caramel, roasted peanuts, and milk chocolate. If you're like me and didn't know what nougat is, it's a mix of sugar, protein, and fat. Caramel is made from melted sugar and milk chocolate combines cocoa, milk, and sugar. The roasted peanuts are specially treated to ensure the perfect crunch. Every ingredient is top-notch. For example, peanuts are purchased in massive quantities and carefully sorted so only the best nuts make it into the bar. Let's take a closer look at the ingredients. Nougat forms the base of the bar. It's made in giant mixers where sugar, glucose syrup, egg whites, and fats are whipped together. Flavorings are added to give the nougat its distinctive taste. The finished nougat is rolled into long ribbons. This process of rolling nougat into ribbons is a true demonstration of engineering mastery. The soft, warm nougat is handled by special machines. First, the nougat is loaded into an extruder, a machine that pushes it through openings to form long, uniform strips. Think of it like a giant piping bag at a bakery, but on a factory scale. Pressure and temperature are carefully controlled to keep the nougat pliable but intact. After extrusion, the ribbons move onto a conveyor belt where rollers even out their thickness. These rollers are like massive kitchen rolling pins that gently press the nougat, ensuring consistent thickness throughout the ribbon. To prepare the nougat for the next steps, it's cooled using ventilation systems or cooling plates under the conveyor. For Snickers, the nougat is cooled to the perfect temperature, elastic yet non-sticky. This step slightly hardens the nougat, making it easier to apply the caramel layer. The width and thickness of the ribbons are adjustable depending on the bar size. For instance, thinner ribbons are made for Snickers Mini compared to the standard size. Once ready, the nougat is either cut into portions or processed further with caramel and peanuts. And just like that, every Snickers bar begins its journey as a smooth ribbon of nougat. After the nougat cools, it's time for the caramel layer. The caramel is heated and evenly spread over the nougat. This layer adds a smooth sweetness to the bar. Applying caramel onto hardened nougat looks almost magical, but it's really the result of precision engineering. Caramel is prepared separately in massive kettles, where sugar, syrup, and milk ingredients are mixed. The mixture is heated to about 280 degrees Fahrenheit, making it flowy, but not too runny. Maintaining a steady temperature is crucial for the texture and quality of the caramel layer. The hot caramel is transported through special pipes to an applicator above the nougat conveyor. Picture this, it's like a chef drizzling sauce, but on an industrial scale. The caramel flows through special nozzles or combs, which spread it perfectly over the nougat ribbons. These nozzles ensure just the right amount of caramel is applied. No gaps, no excess. Sometimes, tools like blades or vibrating mechanisms smooth out the caramel to perfection. Once the caramel is applied, the ribbons move into a cooling chamber, where the caramel hardens just enough to create that soft yet firm texture we love in Snickers. The temperature in the chamber is carefully controlled to prevent sugar crystallization. The caramel layer isn't thick, but its amount is calculated to balance perfectly with the nougat's flavor. This is one of the secrets behind Snickers' harmonious texture. After cooling, the caramel becomes a stable base for the next step, adding peanuts and finally the chocolate coating. The third layer is peanuts. Each Snickers bar contains about 16 whole peanuts, evenly scattered on the caramel base to ensure every bite is crunchy. The peanuts used for Snickers undergo strict selection. Only perfectly whole, roasted and shelled nuts make it to production. The peanuts are roasted to a golden brown to enhance their flavor and crunchiness. They're sorted by size, and any broken or tiny pieces are removed because Snickers is known for its big, bold peanut chunks. The prepared peanuts are delivered to the production line through hoppers, large containers that act like giant dispensers. These hoppers automatically measure out peanuts to ensure each section of the caramel ribbon gets an even portion. Dispensers above the caramel ribbons work like massive sieves, evenly sprinkling the peanuts to create a dense yet orderly layer. Sensors above the conveyor check that the peanuts are distributed evenly. If any spots are missing peanuts, the system automatically adds more. Once the peanuts are in place, the ribbon is briefly cooled. This cooling step sets the caramel enough to lock the peanuts in place for the next step, chocolate coating. Coating the bar in chocolate is the ultimate moment in Snickers production. First, you see the chocolate waterfall, a cascade of warm, glossy chocolate flowing like a miniature fountain. The chocolate is kept at an ideal temperature of about 113 degrees Fahrenheit in giant tanks. This ensures it's liquid enough to coat the bar, but thick enough to form a solid layer. As the bars pass under the chocolate curtain, they're completely enveloped from all sides. Think of it as giving each bar a delicious chocolate jacket. Excess chocolate is collected by a system beneath the conveyor and recycled back into the tank, like a chef carefully reusing glaze. The most spectacular moment comes next. To create the signature texture on the surface, a special comb or fine-toothed blade passes over the chocolate, forming those familiar wavy patterns. It looks like the chocolate is dancing to the conveyor's rhythm. After the chocolate coating, the bars enter a cooling tunnel. Streams of cold air harden the chocolate, transforming its glossy surface into the firm, matte shell that cracks perfectly with every bite. On average, the Snickers factory produces up to 500 bars per minute. The final step is packaging. The bars are wrapped in foil to keep them fresh and packed into cardboard boxes. From there, they're shipped to warehouses and distributed to stores worldwide. When the bars exit the cooling tunnel, they line up on a long conveyor belt, like a parade, moving toward the packaging station. It's crucial each bar stays in place because the entire process is automated, and every step counts. Next, they head to the wrapping machine, which operates at lightning speed. Shiny foil sheets, not only to protect the bars, but also to give that satisfying crinkle when unwrapped, are cut to size and wrapped around each bar within seconds. The wrapping is so snug, it seals the bar perfectly, like dressing it in its little suit. After wrapping, the bars pass under cameras and sensors that check for flaws. Any defective bars are removed for recycling because quality is non-negotiable. Finally, individually wrapped bars move to the packing machine, where they're grouped into sets, usually 6, 12, or 24. Robotic arms stack the bars into boxes with precision, like playing Tetris. Boxes are sealed with strong tape, stamped with production dates and batch numbers, and loaded into large transport containers. Robotic platforms stack these onto pallets wrapped in stretch film for extra protection. These pallets are then shipped to warehouses and distributed worldwide, from massive supermarkets to small convenience stores. On modern production lines, tens of thousands of Snickers bars are packaged every hour. The process is so automated, human involvement is only needed for oversight. Before the bars hit store shelves, they undergo strict quality control. Visual checks ensure each bar looks flawless, weight tests confirm they meet standards, and, yes, taste tests ensure they're as delicious as ever. Admit it, you're tempted to apply for that job now, aren't you? There are more than 5 trillion pieces of plastic floating in our oceans, and this number keeps growing every single day. Turning trash into something useful isn't just a creative idea, it's an absolute necessity. This approach not only reduces harm to nature, but also proves that even the worst garbage can have a second life. Imagine this, that waste could be turned into something as stylish as sneakers. Surprised? Well, let's dive into this fascinating journey together. First, you need to find the trash. Specialized organizations rely on advanced collection systems to do this. Hunting for ocean trash is an impressive and highly technical process, using cutting-edge tools designed to capture plastic. One of the most renowned organizations tackling this issue is the Ocean Cleanup. They deploy massive floating barriers that are strategically placed in ocean currents, where plastic waste tends to accumulate in large garbage patches, zones of concentrated trash. Here's how these traps work. Large floating structures equipped with nets or barrier walls move through the water, capturing plastic that drifts into their range. These systems are designed to catch plastic debris floating on the surface, as well as some submerged deeper in the water. Imagine enormous nets gliding smoothly through the ocean, sweeping up all kinds of waste in their path. Once the trap is full, it's hauled to a specialized vessel, where the collected plastic is unloaded. This is done using massive mechanical cranes or conveyor belt systems. The unloaded waste is then sorted and cleaned to prepare it for recycling. These technologies don't just clean up our oceans. They create opportunities to repurpose plastic into new products like textiles, sneakers, and even construction materials. The sight of machines pulling massive piles of trash from the water is both inspiring and a little shocking. Plastic of all shapes and sizes, bottles, bags, broken fragments, and even old toys is brought ashore for sorting. It's a stark reminder of the scale of the problem, but also a glimpse of the incredible potential for change. Once the trash is unloaded onto the ship, it's transported to the nearest port. On land, specialized facilities equipped with conveyor belts and robotic sorting systems take over the next stage of processing. Here, the waste is sorted, cleaned, and prepared for recycling. The process moves at an incredible pace. Robotic arms sort the plastic by type, like assembling a massive jigsaw puzzle. This isn't just random sorting. Advanced technology can detect even the tiniest pieces of plastic. After sorting, the trash gets washed. Much of it is covered in algae or other organic matter, so cleaning is a messy but absolutely crucial step. Sorting is followed by a multi-step washing process. First, the waste is rinsed or scrubbed to remove large contaminants like sand or dirt. Mechanical systems, such as conveyor belts, move the trash through brushes or nets that scrape off big debris. Next, the smaller impurities like oil residues or fine dirt are removed. This can be done in several ways. For instance, as the trash moves along a conveyor belt, high-pressure sprayers rinse it with water. The jets dislodge grime, organic residues, and oil stains. Another method involves submerging the waste in water tanks. These tanks often feature circulating currents, which enhance the cleaning process by gently agitating the plastic and rinsing away remaining dirt. To tackle oil contamination, the plastic is treated with specialized cleaning solutions or chemicals that break down petroleum products and other stubborn pollutants. After these stages, the plastic is finally ready for recycling or disposal. The water used in the cleaning process typically undergoes filtration, so it can be reused or sent for purification to reduce environmental impact. This precise and efficient system ensures the waste is clean and ready for the next step, with adjustments made depending on the material type and its level of contamination. The process of shredding and melting cleaned ocean plastic is truly mesmerizing. A real choreography of technology where each step amazes with its scale and precision. Enormous machines, resembling giant blenders, slice, grind, and crush the plastic into tiny granules. These powerful devices, equipped with massive blades and cutting tools, work at incredible speeds, creating an artificial snow of microscopic plastic particles. As mentioned earlier, the scale of this operation is astonishing. These machines can shred over 1,000 pounds of plastic per hour. The shredded material is ground into granules, which are then sent for melting at temperatures around 500 degrees Fahrenheit. For context, this is the point at which most types of plastic begin to melt and become pliable for reshaping. The roar of massive grinding discs and the compressed sounds of mechanical force fill the air as the plastic is transformed into tiny granules that shoot through the air. Different types of plastic are blended and shredded into a uniform mass. This isn't just waste, it's raw material, ready to be turned into something new. While the granules vary in size, each one is precisely prepared for the next step. melting. These shredded particles are then sent into industrial furnaces for a dramatic transformation. The melting process is comparable to dough that starts off hard and crumbly, but becomes soft and elastic under heat. Gigantic furnaces, heated to extreme temperatures, melt the plastic into a thick, almost liquid state. This molten plastic flows through pipes, gleaming under factory lights like a fiery river coursing through the corridors. In that moment, everything around feels almost magically alive. The melting technology is much like what happens when chocolate or wax is melted into a liquid form. Plastic doesn't just soften, it becomes flexible and easy to shape. At this stage, it's ready to be molded into new items. This semi-liquid material, balanced between solid and fluid states, represents the start of something new, a material reborn to re-enter the cycle of life. As the molten plastic cools, it hardens and takes shape, transforming into products that become part of our everyday lives. This is one of the most captivating stages of recycling, where simple trash turns into something useful, once again finding its place in the world around us. Adidas, Parley for the Oceans, and other brands are already turning ocean plastic into stylish products. For example, making sneakers out of this plastic looks like something straight out of a futuristic lab. Liquid plastic is poured into molds, where it hardens to form the perfect sole. The upper part of the shoe is woven from recycled plastic threads, a kind of textile wizardry that transforms trash into a fashionable accessory. Here's a fun fact. Producing just one pair of sneakers can use up to 11 plastic bottles. These sneakers are not only stylish but also eco-friendly, utilizing materials that might have ended up polluting our oceans. On a large scale, recycling plastic helps reduce dependence on virgin resources. For instance, recycling 1 ton of plastic cuts carbon dioxide emissions by as much as 1.5 tons. One of the biggest names in sportswear even created jerseys for soccer teams, including Real Madrid, made from plastic retrieved from the ocean. Now, players are quite literally wearing the ocean during their matches. What about construction materials? This is another equally fascinating avenue. Plastic granules are mixed with sand or other materials to create durable panels for construction. Ever considered that your home could be partly built from recycled trash? This is becoming a reality, not only reducing the amount of plastic in our oceans, but also cutting carbon emissions in the construction industry. In New Zealand, plastic bottles are being turned into synthetic sand for building roads. This sand is significantly cheaper and more eco-friendly than traditional options. Here's a staggering statistic. Every minute, more than 2,000 plastic bottles enter our oceans and seas. Only about 9% of all plastic waste in the environment is properly recycled. The rest ends up in landfills or the ocean, leaving us with serious concerns about the planet's future. But there's good news. Recycling ocean plastic isn't just about helping nature. It's also a booming business. For example, one company specializing in ocean plastic recycling processes over 22 million pounds of plastic each year, transforming it into sportswear and accessories. In the fashion industry alone, more than 500 million plastic bottles are reused annually to create new products. Many companies are repurposing old fishing nets, which pollute the oceans, into sneaker soles. These fish catchers are now turning into eye catchers when you slip on these stylish kicks. Some companies even craft trendy chairs from ocean plastic, including discarded fishing nets. The irony? These nets used to catch fish, and now they sit in restaurants. Think batteries are just boxes that store power? What if I told you it takes nearly 375 tons of rock and over 528,000 gallons of water to produce a single electric vehicle battery? Or that 70% of the world's cobalt is mined under terrible conditions, sometimes by children? In this video, you'll learn not just how lead-acid and lithium-ion batteries are made, but also the environmental impact they leave behind. Ready for some shocking facts that will change the way you see batteries? Let's get started. Car batteries are the heart of modern vehicles. They power the engine start, fuel electrical systems, and in the case of hybrids or electric vehicles, are the primary energy source for motion. But let's dive into their origins. The story of batteries begins back in the 18th century. In 1800, Italian scientist Alessandro Volta invented the first chemical battery, known as the voltaic pile, a far cry from the rechargeable batteries we know today. The first rechargeable batteries were created by French physicist Gaston Planté in 1859. These were lead-acid batteries, and remarkably, they're still widely used in vehicles with internal combustion engines today. The modern production of car batteries is a complex, multi-step process that requires precision and strict quality control. Let's break down the details using the most popular types: lead-acid and lithium-ion batteries. For lead-acid batteries, the primary materials include lead, lead dioxide, sulfuric acid as the electrolyte, and polypropylene for the casing. Lead is either mined from ore or recovered from used batteries. It's then purified and melted for further use. Recovering lead from old batteries is a process that combines engineering expertise with a touch of modern-day alchemy. First, old batteries are dismantled, crushed in specialized machines, and sorted into lead, plastic, and electrolyte components. Think of it as a high-tech blender that breaks everything down into its core ingredients. The lead components are sent to smelting furnaces, where they're heated to temperatures exceeding 1,100 degrees Fahrenheit. At this stage, the metal transforms into a shiny silver stream that's mesmerizing to watch. Impurities and slag are separated, leaving behind pure lead, ready for new uses. The purified molten lead is poured into molds, where it cools and solidifies into perfectly uniform ingots. These ingots form the foundation for new batteries. The most fascinating part? This lead can be recycled endlessly. It has already lived in previous generations of batteries and might just end up powering your car. Lithium-ion batteries are made from key components like lithium, nickel, cobalt, manganese, graphite, and an electrolyte. Lithium is sourced either from salt flats in South American countries like Chile and Argentina, or from ore deposits in Australia. For lead-acid batteries, the electrodes are crafted from lead plates coated with active materials, specifically lead powder and lead dioxide. Picture this. Molten lead is poured into molds or rolled into thin sheets, which are then cut into precise shapes. These plates often feature multiple holes or grids to enhance bonding with the active material. The active material, which coats the grids, is prepared as a thick paste made from lead powder, water, sulfuric acid, and additives that enhance the chemical reactions. Let's take a closer look. The powder is produced by oxidizing lead in specialized mills, which grind it into a fine dust with the required properties. Watch as the grids move seamlessly along an automated conveyor, where the paste is applied to both sides. Rollers in the machine press the paste into the grids with just the right amount of force, ensuring even coverage and deep penetration into the cells. Excess paste is scraped off with blades, leaving a perfectly smooth layer. These paste-coated grids are then sent into special drying chambers. Inside, the paste loses moisture and hardens, transforming into the active material. We've covered lead-acid batteries. Now let me show you how lithium-ion batteries are made. In lithium-ion batteries, the anodes are made from graphite, while the cathodes are crafted from metal oxides, like lithium cobalt oxide. Next comes the assembly of the battery cells. These are the basic building blocks of the battery. In lead-acid batteries, cells are made by stacking several plates separated by separators. In lithium-ion batteries, the cells can be cylindrical, prismatic, or in pouch cell form. Electrolyte filling is the next step. In lead-acid batteries, a sulfuric acid solution is poured in. For lithium-ion batteries, an electrolyte made from organic solvents ensures the transfer of ions between the electrodes. The finished batteries undergo an initial charge to activate the chemical reactions. Each battery is tested to ensure it meets key parameters such as voltage, capacity, and resistance to discharge. Lead-acid batteries are then encased in polypropylene shells. Lithium-ion batteries, on the other hand, are often assembled into modules, which are later integrated into large battery packs for electric vehicles. Battery production is an energy-intensive process with significant environmental impacts. While lead can be smelted and reused, plastic casings are recycled into new shells, and the electrolyte is neutralized or processed. The situation with lithium-ion batteries, however, is far more challenging. Only about 5% of lithium-ion batteries are recycled. This is due to the complexity of extracting lithium, nickel, and cobalt. But the damage doesn't stop with neutralizing the components. To produce a lithium-ion battery for an electric vehicle weighing about 1,100 pounds, it takes 550,000 pounds of rock and nearly 530,000 gallons of water. This depletes Earth's precious resources. Producing just one EV battery generates anywhere from 3 to 16 tons of carbon dioxide. Imagine that. This is the same amount a gas-powered car emits over 5 years of driving. And that's just from one battery. The most troubling issue, however, is cobalt mining. About 70% of the world's cobalt comes from the Democratic Republic of Congo, where workers, including children, labor under horrific conditions. According to Amnesty International, more than 40,000 children are involved in cobalt mining. To make matters worse, mining often destroys local ecosystems, leaving lasting environmental damage. Recycling lead-acid batteries in countries with low environmental oversight, such as India and China, presents its own set of dangers. Lead dust and acid emissions often escape into the air, creating toxic clouds that harm the health of hundreds of thousands of people. Imagine this. One ship contains up to 20,000 tons of steel. That's the weight of 3 Eiffel Towers. But what happens when these ocean giants retire? Every year, more than 1,000 vessels are sent for recycling, and their materials find new life in bridges, cars, and even other ships. This isn't just dismantling, it's giving metal a second life. Stick around to see how this global process is changing the world. The beginning of the end, or why are ships dismantled? Ocean vessels have an expiration date. On average, that's about 25 to 30 years. After this, maintaining them becomes uneconomical and their structures unsafe. This is where a process, often called shipbreaking, begins. Remember those movie scenes where ships are shattered by waves? Well, no waves are needed here. Just welding tools, massive cranes, and teams of workers who know how to handle these metal giants. First, everything is stripped from the ship. Furniture, electronics, pipes, and cables. Even doors and windows. All of this can be recycled or reused. This process is usually carried out by hand, though sometimes specialized equipment is used. Workers physically dismantle the interior of the ship, unscrewing bolts, cutting metal pipes, removing doors, windows, and panels. It's meticulous, labor-intensive work, requiring attention to detail and strict safety protocols. Imagine this. Cables need to be carefully extracted so they can be sold as copper scrap, and chemicals, such as leftover paint or lubricants, must be safely removed. Even furniture is taken apart to salvage wood or metal components. Of course, on large shipyards, workers are aided by mechanical tools, cranes, gas cutters, and sometimes robots to handle hazardous materials. But the bulk of the work is manual labor. That's why, in countries like Bangladesh or India, where labor is cheaper, shipbreaking is so popular. This stage is crucial because properly preparing a ship for dismantling prevents leaks of chemicals and toxic materials that could harm the ecosystem. Oil, fuel, and chemicals all are drained from the ship to avoid environmental contamination. Once the ship's hull is stripped of everything unnecessary, the gas cutters take center stage. Massive, rusty steel walls, the very structures that once kept the ship afloat, are gradually turned into individual pieces of metal. Workers, dressed in protective suits, stand directly on the hull. Their cutters create bright orange sparks, flying in all directions, producing a kind of steel fireworks. It's both mesmerizing and slightly intimidating. The cutter heats the metal to such a high temperature that it literally melts. But it only looks easy. Ships aren't just piles of steel. They're labyrinths of multiple layers of metal. Sometimes workers have to cut through several layers to reach the right spot. Cutting begins with the upper decks. Large sections are first carved out, like chunks of sidewalls, decks, or even parts of the hull, which are then lifted by cranes and loaded onto platforms. From there, they're sent to factories, where the pieces are recycled into new steel or aluminum. But it's not just about cutting, it's about doing it safely. That's why the hull was cleared earlier of any leftover fuel, lubricants, or other hazardous materials. Without this step, gas cutters could trigger explosions. So, this process is not just labor, it's an art that requires strict adherence to safety rules. And of course, all this happens under the blazing sun or in humid coastal climates. Workers quickly adapt to the heat, and even sparks flying at their feet become a routine sight. In the end, they witness the transformation of a massive, once indomitable ship into mere pieces of metal. It's almost like watching a rebirth. Imagine this. Those massive steel blocks that once kept a ship afloat become the foundation for new bridges, buildings, or even other ships. About 90% of a ship's materials can be recycled, and the largest share is steel. A single large ship can yield up to 20,000 tons of this metal. That's the equivalent of 3 Eiffel Towers in weight. Once the ship's hull is cut into pieces, the next thrilling phase begins, transporting the steel to factories. And trust me, it's not as simple as throwing it on a truck and driving off. These metal pieces are usually so large and heavy that they can't be moved by conventional means. Massive cranes, the kind that look like they could lift a ship themselves, dominate the scene. Their long metal arms with hooks or magnetic platforms carefully grab steel sections and lift them off the ground. It's almost like watching giant toys in action, but everything is done with surgical precision, because one mistake could be costly. After that, the steel is loaded onto huge platforms or special trucks. Regular trailers won't cut it here. You need vehicles with reinforced frames capable of bearing tons of weight. Imagine this. One section can weigh several dozen tons. Sometimes, rail cars or barges are used for transport if the factory is near a port or river. This helps cut down on delivery costs because moving steel is no cheap task. The journey to the factory can be long. For example, if a ship is dismantled somewhere in South Asia, its materials might be sent as far as Europe or America. In such cases, the metal is loaded onto ships again, but this time on cargo vessels. Full circle, right? A ship becomes raw material transported by another ship. Once at the factory, the metal is carefully weighed. Every detail matters, from the total weight to the precise composition of the metal, as different alloys require different processing. Only then does the steel head to the melting stage, where its new life begins. This steel will become new construction materials. Ships continue their legacy, not in the ocean, but as skyscrapers or train tracks. But it's not just steel that's valuable. Ship components also contain aluminum, used in car and airplane manufacturing. Wooden elements, rare in modern ships, but present in older ones, are restored and sold for decor. Fabric from old seats is sometimes repurposed into bags or even rugs. Isn't that cool? You buy something stylish and later find out, oh, this was on a liner that sailed the Caribbean. But it's not all smooth sailing. Ship recycling can pose environmental risks if done irresponsibly. Ever heard of Alang? It's the world's largest ship recycling yard, located in India. There, ships are literally beached and dismantled by hand. This method is cheap, but dangerous. Oil and chemicals can leak into the water, and workers often lack proper protective gear. Recently, however, the world has started paying attention to this issue. More and more ships are being recycled at specialized yards that follow strict environmental standards. For instance, in Europe, regulations require the safe storage and disposal of hazardous materials. The largest ship ever dismantled was a container vessel measuring 1,312 feet in length. Imagine taking apart such a giant. This container ship, Ever Given, became famous in 2021 after blocking the Suez Canal, though its end wasn't due to that incident. When ships of this scale are retired, they're usually sent to one of the world's biggest shipbreaking capitals. Dismantling such a vessel likely took no less than a year, because a mountain of steel, cables, equipment, and other materials is a serious challenge, even for experienced teams. Every piece must not only be cut, but also carefully moved, sorted, and shipped for recycling. At the steel plant I visited, everything starts with thoroughly inspecting the metal pieces. They're cleaned of any paint, rust, lubricants, or other impurities that could affect the quality of the steel. Watch as dozens of hands and machines work to prepare this metal for its next journey. Next, the pieces are shredded, cut into smaller parts that are easier to load into the smelting furnace. The process of cutting metal at steel plants is a spectacle in itself, like something out of a sci-fi movie. Huge workshops filled with sparks, heat, and the hum of machinery. These aren't ordinary scissors. They're powerful hydraulic presses, cutting machines, and even lasers. Each tool plays its part depending on the size and type of metal. First up are hydraulic shears. These massive machines can slice through thick steel like paper. They operate under immense pressure, thousands of tons of force that literally crush and cut the metal. Their crunch echoes throughout the workshop. For finer work, gas or plasma cutters are used. A gas cutter operates by burning fuel. Oxygen and acetylene heat the metal until it melts, and then a stream of gas cuts through it. Plasma cutters are even cooler. They create an electric arc that melts the metal, leaving a clean, precise edge. Then there are laser machines. They work with incredible precision, carving out the tiniest details. The laser beam seems to dance across the metal's surface, leaving behind a smooth, polished cut. This is the technology of the future, already in action at many factories. But this isn't just random cutting. Every step is carefully planned. Metal is sorted by thickness and type to avoid damaging equipment. Larger pieces go through specialized conveyors to the next stage, while smaller ones are sent straight to melting. For melting steel, arc furnaces are used. These massive monsters run on electricity, generating temperatures close to 3,000 degrees Fahrenheit. The metal simply melts, transforming into liquid steel. But that's not all. Special substances, known as ferroalloys, are added to the molten mass to enhance the steel's properties. Need strength? Add vanadium or chromium. Want it lightweight? Add aluminum. It's like cooking, but for engineers. Next, the steel is poured into molds, depending on what it's destined to become. These could be sheets, beams, rebar, or even wire. The castings are cooled, cut, polished, and then shipped off for new projects. Building skyscrapers, bridges, or even new ships, all of this can start with the recycled hull of an old vessel. And isn't it amazing? A ship that once carried thousands of tons of cargo across oceans can become part of a car or the frame for a modern stadium. This second life of steel feels almost magical, doesn't it?